Hello everyone. So I welcome you again in this lecture and today we are going to talk about M-way search tree. Already we have discussed about search trees like binary search tree we have discussed in our previous lectures. Now binary search trees are also called as two-way search trees. Now this is a new form of search trees and the name is M-way search trees. So we'll talk in detail that what is M-way search trees and how they are different from binary search trees. Now in the binary search trees, we have seen that it's a binary tree in such a way that it holds the order property. In the binary search tree, we have a left child and the right child. The left child are kept in such a way so that it can be less than the root, and the right child are kept in such a way that the values or the key values in the right tree is always more than the root. Now, because it's a binary tree, so definitely it means that every node can have maximum two child. So if we talk about a binary search tree, we have this kind of notations where we write the value here. Let's say this is x1, this is x2, and this is x3. Then x2 is less than x1 and x1 is less than x3. This is what we used to keep. Now here you can see that the node is having one value and then it has two child, that every node will have one value and can have two subtrees. This is what we have seen in the binary. Now here the maximum subtrees for any node can be 2 and it is said to be two-way trees. Similarly, if we make possible for any node which can have m subtrees, then that tree is said to be m-way such trees. Now here when we say two-way tree, in the two-way tree every node is having 2 minus 1 value, that is uh, one value, right? So in the case of m-way search tree, we have m subtrees and every node can have m minus 1 values. So here you can see that in the binary search trees we have only one value at each node and have two subtrees, and based on this we can generate the idea of m-way search tree, which is also defined the same way. So here in the m-way search tree we have m minus 1 values per node and can have m subtrees. Now m is called the degree of the tree. So when we say binary search tree or a two-way search tree, the degree is 2. Similarly, when we talk about the m-way search tree, the degree of the tree will be m. So in the binary tree, the degree is 2. Now, it is not necessary for every node to contain exactly m minus 1 values. Now, when we talk about the two-way trees, a node contain at least one value, and this is actually the maximum and minimum limit when we talk about the binary search tree. But when we talk about the m-way search trees, every node can have m minus 1. So this is the maximum limit. It means that node does not contain exactly m minus 1 values and does not have exactly m subtrees, but this is a maximum possible subtrees that a m-way search tree can have. In an m-way search tree, a node can have anywhere from 1 to m minus 1 value. So the minimum values in any node of the m-way tree is 1 and the maximum to m minus 1. The number of non-empty subtrees can range from 0 to 1 plus number of values. So if a node is a leaf, then it does not have any subtrees, then it has 0 subtrees if it is a leaf. Otherwise it will have 1 plus number of values. What does that mean? It means if any node is having 2 values, that means it has 3 subtrees. If any node is having m minus 1 values, then it will have m subtrees. M is thus a fixed upper limit on how much data can be stored in a node. So here M is actually giving you the upper limit. Okay, now let us talk about more properties of this M based search tree. Now, the values in the node are stored in ascending order because it's a, a search tree. Already we have discussed that binary search tree is a tree which follows the order property. Order property means the values which are stored in the node maintain some property of ordering, like the left subtree will always be having less values than the root node, and the right subtrees will have the values more than the root node. So here you can see that the values which we are keeping in the node of MWeight tree will be kept in order, in the ascending order. That means from left to right the values will be increasing. So if any node contains values v1, v2 up to vk, where vk we are assuming it is less, it is a maximum m minus 1, then they are kept in such a way that v1 is less than v2, v2 is less than v3, and so on is less than vk, and subtrees are placed between the adjacent values, and the subtrees are actually placed between these range. So when I say v1 and v2, this is actually one value, and the subtrees are actually placed between these with one additional subtree at each end. So if there are if you say this is x1, x2, x3, then you can find values in between, means the subtrees can be here, subtrees can be maybe can be here, and at in the between and at the last. So what you will observe, you will observe that for the three values we have four subtrees. So always subtrees are always more than one value. Okay, so here you can see. So we have taken an example of three-way search tree. When I say three-way, that means a node can have maximum three subtrees and two values. So here you can see this is a node for a three-way search tree. You can also say that two-way trees are also a kind of M-way search tree, but when we talk about M-way search tree, it is a generalized notation which is actually applicable for values more than 2. So if M is 3, then it means that a node can contain 3 subtrees with 2 key values at each node. So if I say if M equals to 5, that means the node can contain 5 subtrees and each node will have 4 values. So when we talk about the M-way tree, so this is the simplest tree that we can think about, because a two-way already is a binary search tree. Then we have three-way, four-way, five-way, and so on. So the very simplest to assume is the three-way search tree. So here we have taken an example of three-way search tree just to understand that how these trees are represented. This is the simplest form of M-way search tree where m equals to 3. So you can see here that every node is having maximum 2 values and can have 3 child. So this is just we have taken to understand that how it can be represented, but in the real life m is basically representing our very large values. So here each node corresponding to a physical block on disk. So m represents the maximum number of data that can be stored in a single block. So just keep in mind that block is the basic entity that is actually stores our data. Like when we talk about Excel sheet, so in the Excel sheet the cell is the very basic entity that actually holds the value, and cell is represented by using the row and column. So in computers, when you are storing the data, block is a very basic storage which actually stores your data, which holds your data, and block is actually represented using the track and sectors. You might be knowing that your hard disk is actually composed of tracks and sectors. Then this track and sector basically defines the block, and so the basic is a very fundamental. So the block is a very fundamental unit of storing your data. So whenever you want to access your data, you need to access the blocks. So M basically represents the maximum number of data items that can be stored in a single block. So that also means that M is, we are trying to maximize the M so we can speed up the processing, because whenever you want to access data in your computer, data has to be retrieved from the hard disk. So when you are accessing data which is placed on the memory in the RAM, it is very fast. But whenever you want to access data from the hard disk, the operations become slow. So we want to come up with some strategy that we want to have minimum access to the hard disk so that our entire process can be fast. So we'll see that how all this structure can be used to make the entire functioning fast. Let us see that how the things works in the MWave search tree. So first let us look at how the searching can be done in this tree. Here I am assuming that you are already familiar with the binary search tree and you know that how the searching can be done in binary search tree. We will use the principle of binary search tree because binary search tree is also a two-way search tree. So we will use the principle, and using that principle we will add some more operations to it to get our tasks done. If we are searching a value x and currently at node consisting in the values v1 to vk. So let's say you are looking for any value x which actually exists at any node which contains value v1 to vk, because we know that in the MWave search tree a node consists of multiple values. Like in the binary search tree, only a single value is existing at any node, so you just go to the node and look to the value of that node and you are able to decide that the node contains the value or not. But here every node consists of number of values and you need to look for each of these values. But again, between the values we have a subtrees, so we will see that how the things can be done. Now, in order to proceed for searching the operation, we need to look to some cases. There are basically four cases arises. If x is less than v1, now v1 is the, so we are assuming that this is a node where x is existing, and along with x we have some more values are there, v1, v2, then we have x, v3, v4, something like this. Now, you are searching some value x. Now, if x is less than v1, recursively search for x in the v1 left subtree. So as you know that this is also a ordered tree where the values are arranged in such a way that the left side contain the value less than the node and the right side contain the values more than the node. So if the value which you are searching is the less than the very first value of the node, that means the value which you are searching will be a part of the left subtree. So you have to recursively apply the procedure in the left subtree to search for x. If the x which you are searching is more than the last value of this node, which is vk, so if it is happening, that means definitely that x is a part of a right subtree, and then you have to recursively apply the same procedure of searching in the right subtree. Now if x equals to vi, if the value which you are searching is one of the value which actually exists in this node, then you are actually done. You will stop and you will return the value x, and you may means print that value has been found. The only remaining possibility is that v some I vi is less than x, and x is less than vi plus 1. So here the fourth case means that the x is not less than the very first value, x is not less is not more than the very last value, and x is also not a value which actually exists in this node. So the other case is possible is that x is somewhere existing in between the two values. So let's say v1 and v2 are two values and your x is in this between the two values. In this case, what you will do, you need to look to the subtree which exists in between the two values, and then recursively you have to apply the same procedure that we have discussed so far. So here we have realized that the searching is not the very straightforward that we have discussed in the binary search tree, but here we have to do some more exercise to get our value, find out if it is existing in the tree. Now so far we have understood that what is the purpose of writing more values, because if you write more values in one node, then we are actually able to reduce the number of such operations, and we also able to reduce the height of this tree. So both will this impact the accessing of the blocks of the hard disk, because whenever you are accessing any block, the entire block will be retrieved and kept in the RAM, and you are actually able to search a lot of values at one fetch. If you are keeping only one value at each node, then every time when you fetch a node, you are only able to get one value. But if a node consists of multiple values, that in every fetch from the hard disk to the RAM, you are getting multiple values, and this is how we can somehow reduce the number of access or read operations from the hard disk. Now let us talk more about the MWay trees. It has following properties. Each node has 0 to m subtrees. Now there are the possibilities that a node is a leaf and it does not contain any child or subtrees. So it can have either 0. If it is a leaf, it will has no subtrees, then in that case it has 0 subtrees, or maximum it can have m subtrees. Now this is the only possibility when the node already consists of m minus 1 values. A node with k less than m subtrees consists of k minus 1 keys. So already we have discussed that whatever the number of trees any node is having, it will have one less than the number of subtrees in its node. For example, if a node consists of 3 subtrees, that means this node is having 2 values. The key value of the first subtree are all less than the key values. So because we know that this is the order tree, and the values are placed in such a way that the left tree will always be less than the key values at the root. So the key values of the first subtree, so whatever the values are having in the first subtree, will all less than the very first value of this node. The data entries are ordered. Yes, this is also following the order property. All subtrees are M-way trees. Now this property is applicable to the entire tree in all the subtrees as well. Every node will fulfill this criteria, that every node can have maximum m minus 1 keys and can have maximum m subtrees. As with binary search trees, inserting values in ascending order will result in degenerate M-way search tree. We have seen that binary search trees are ordered trees, but they are not balanced. So if you are inserting values in ascending order, you may get a tree which may be extending towards one direction. For example, if I'll take example of inserting the key values, let's say 2, 9, 16, 32, and then let's say 40. So if I construct a binary search tree out of these key values, then my tree will be going to like this: 2, 9, 16, 32 and 40. So you can observe here that binary search trees are not compulsory balanced. They may be extending towards one direction, so they may got degenerated. Similarly, the M-way search tree can also be degenerate, and the height of the tree can go up to order of n instead of log n. Now log n is a scenario when we are able to make our tree balanced. So M-way search tree is also not a balanced tree, and there is a possibility that if the keys are inserted in a ascending order, then it may be extending towards one direction, and this may make the tree of this much order. Now we always want to make our tree balanced so that the height will be log n. Now why we want to keep our tree maintain the minimum height or keep the log n height? Because the operations which we are doing on the trees are based or described in terms of the height. So whenever you do operation like inserting an element, searching an element, modifying an element, deleting an element, this all depends on the height of the tree. So we always want to reduce the height of the tree, and this is only possible when we keep our tree balanced. So One solution to this problem means if your tree is extending towards one direction, then we can make our tree balance. And already we have discussed the AVL tree. So AVL tree is one of the method or one technique through which we can make our binary trees, binary search tree as a balanced tree. So here we need to have some mechanism so that this MV trees can also be balanced, so that the complexity of all the operations may be reduced. We have discussed about the properties of MV trees. So far, I believe that you have understood that what is MV trees, what are its properties, what are the drawbacks. So drawback, we have identified that MV tree can be extended to one direction and it may increase the complexity. So we need to come up with some, we need to look to some mechanism, like we discussed AVL trees for balancing. We have to look to some method that can make our binary this MV trees as a balanced tree. So we have a mechanism or a structure that will try to make the tree balanced and reduce the complexity of these M-based search trees operations. And the tree is said to be B trees. So in the next lecture, we are going to talk about B trees. This is all for this lecture. Thank you very much.